Hello everyone. इस वीडियो में we have taken up a question on the oscillation of a capacitor plate. So the problem statement goes as such that there are two metal plates with area S and mass m. One plate is situated at top of the other one. Plates are connected to each other with springs whose total spring constant is K and are made of insulators. The lower plate is mounted on a steady base. The equilibrium distance between the plates is x naught. Neglect gravity. So the first question says that initially the battery is not connected between the plates. Now if the upper plate is slightly displaced vertically from the equilibrium position, then find the angular frequency of small oscillations of the plate. And the second part says that now if the battery of EMF V is connected across the plates so that the plates form a capacitor. In the new equilibrium position, the distance between the plates is x1. Now in this case, if the upper plate is displaced slightly from the equilibrium position, find the angular frequency of small vertical oscillations of the plate. So आप इस वीडियो को pause करके you give it a try to this question and then you can come back for the solution part. Okay, so having said that, let us see how we can approach this question. In the first part, the battery is not connected between the plates, and remember that there is no gravity. So initially हम यहाँ पर क्या बोल सकते हैं? Let us say this is our up top plate and this is the bottom plate, and the bottom plate is kept fixed. Okay, it is kept fixed on the ground, and there is a spring between the plates with a effective spring constant as K. Now, if there is no gravity, then I can say that the initial equilibrium position is given as x naught. So the spring must be in the natural length at this position because there is no gravity. So there is no weight which is going to compress the spring. Right. So the initial condition is given to us as that the battery is not connected in the system. So I consider the spring must be in equilibrium position or spring must be in its natural length state initially. So this will be the equilibrium position, initial equilibrium position. Now, if I displace this plate by a small distance x, okay, remember that we displace it by a small distance x. So if you displace this by a small distance x, so the spring gets compressed by a distance x. So I can say there will be a spring force developed, which I can write as K into compression in the spring, which is x. So now this plate experiences a net upward force of kx. So there must be an acceleration of this plate at this instant. So I can write the acceleration as force, which is k into x, divided by the mass of the plate is m. So you can see that the displacement that is given to the plate is in the downward direction, but the acceleration of the plate is in the upward direction. So the displacement and acceleration are in opposite directions. So I can put a negative sign over here. So I can say that acceleration is negative of k by m times of x. So if you compare this equation with the equation of linear SHM, you can say that this term corresponds to the angular frequency square, omega square. So the angular frequency in this first case must be under root of k by m. This must be the angular frequency in the first case. Okay, this was a pretty simple part. Now in the next part, it is said that the battery is connected in this system. So if you connect a battery, what happens? Let us say that this was the capacitor plate, this was the top capacitor plate, and this is the bottom one. Now if I connect a battery across these two plates, the EMF of the battery is V, and definitely I can say that there is some capacitance over here and you have connected a battery, so definitely the plates are going to acquire some charge. Right, they are going to acquire some charge. So if they acquire some charge, then there will be an attractive force between the plates. The lower plate is fixed, so the upper plate is going to move down a bit. So there will be an electrostatic attractive force on this plate. So due to this attractive force, its equilibrium position is going to change. The system's equilibrium position is going to change. So suppose this is our new equilibrium position for this top plate. Okay, so this is our equilibrium position now. Now it is given in the question that after you connect the battery, the equilibrium position is such that the distance between the plates is x1. So what happens at equilibrium position? I can say that net force on this upper plate must be zero in equilibrium position. So the initial separation between the plates that was given to us as x naught, and the new equilibrium position, the separation between the plates is x1. So there is a compression in the spring of x naught minus x1. All right, this distance represents the compression in the spring x naught minus x1. So there will be a spring force in the upward direction, which I can write as spring constant into compression, which is x naught minus x1. Now apart from this, there must be an electrostatic force, which is the attractive force here. So what will be this electrostatic force? Let us say this is our plate 1 and this is the plate 2. So I can say that this electrostatic force will be the charge on plate 1 multiplied by the electric field created due to plate 2. Okay. So the plate area is given to us as S. So I can say that the charge on plate 1 is capital Q and electric field due to plate 2 must be sigma by 2 epsilon naught. This is the electric field due to any one plate. So what is sigma? Sigma is simply the charge on this lower plate divided by the area of this plate. So I can write this expression as Q square divided by 2s epsilon naught. This will be the electrostatic force of attraction between the plates. Now, if this is the equilibrium position, the net force on this plate must be 0. So I can write k times of x naught minus x1 must be equal to q square divided by 2s epsilon naught. Now, what is q? So you can see that in new equilibrium position, the separation between the plates is x1. So I can say that the charge on the plate is simply capacitance multiplied by the potential difference across the plates. So capacitance I can write as plate area into epsilon naught divided by the separation is x1 at equilibrium position multiplied by the potential difference across the plates is V. So this must be the value of Q. So let us put this value of Q in this expression. So this term will be half of S epsilon naught, and in numerator we will get S square epsilon naught square into V by x1 whole square. So this epsilon naught term gets cancelled out. We are left with half of S epsilon naught times of V by x1 whole square. So this is our first expression. Now, if I displace this plate from the equilibrium position, if I displace this plate by a distance x, so you can see that the separation between the plates which was x1 at equilibrium position, this x1 is changing. So if x1 is changing, so definitely the capacitance is going to change, right? So if capacitance is changing and the battery remains connected, so the charge is going to change. So if the charge changes, then the electrostatic force is also going to change. So if you change this separation between the plates, the electrostatic force is going to change. So the electrostatic force, what is the electrostatic force? We have seen over here that electrostatic force is given as half of S epsilon naught into V by x1 whole square. This is the electrostatic force when the separation between the plates was x1. Now let us find that what is the change in electrostatic force if you displace this top plate by a small distance x. So if I find this expression, this will be half of S epsilon naught V square and multiplied by 2 divided by x1 cube times of dx1. So I'm just writing the magnitude of this force. So what is dx1? Dx1 is the change in the separation between the plates, which is equal to x, the small displacement that you have given to the upper plate. So dx1 is simply x. So this value becomes half of S epsilon naught into, you can see over here that this x1 cube, I'm writing this as x1 square multiplied by x. So V by x1 whole square into 2x divided by x1. Right, so I can I'm rearrange this expression. What is the change in this electrostatic force? So this half epsilon naught, half S epsilon naught into V square by x1. So I know this value from expression 1. I can write this as k times of x naught minus x1 times of 2x by x1. So this is the change in the electrostatic forces. So when you are displacing this top plate, the electrostatic force is going to change, and also the spring force is going to change because we have furthered the elongation on the spring by a distance x. So the net restoring force, what will be the net restoring force on this plate? So when you're writing the restoring forces, you need to consider that what are the changes in the force, what are the variable forces that are acting on this plate. So when I'm changing this separation between the plate by a small distance x, definitely the electrostatic forces are changing and also the spring force is going to change. But you can see that the direction of spring force and the direction of electrostatic force is in opposite direction. So for writing the net electrostatic force, I can write them as the difference of these two quantities. So the change in electrostatic force is k times of x naught minus x1 times of 2x by x1 minus the change in the spring force. So change in the spring force is simply k into x. X is the further elongation or further compression that you have created in the spring. So the restoring force due to the spring must be k times the value x. So if I solve this expression, you will get this as k times of, or let us say k into, or I can write this as 2 times of k x naught into x by x1 minus of 2k times of x minus kx. So minus of 3kx plus 2k x naught by x1 times of x. So if this is the restoring force, so what is the acceleration produced due to this small displacement in the plate? So I can write acceleration will be simply restoring force divided by the mass of this plate. So if I take minus of k by m as common, so I'll be left with 3 minus 2 x naught by x1 times x. So you can see that we are getting the acceleration as proportional to the displacement that we have given to this upper plate. So comparing by the equation of linear SHM, you can say that this term in the bracket represents omega square. So the time period or the angular frequency, sorry, which has been asked in the question will be simply under root of k by m times of 3 minus 2 x naught by x1. So this will be the angular frequency in the second case. So you can see over here that this must be option C, right? K by m into 3 minus 2 x naught by x1.